So I'm going to go over the test and talk you through the explanations that you need for each question. So number one, which statement adequately explains what the bond between S and F, sulfur and fluorine, is like? Notice this says with the bond, so it's talking about like one of these bonds, right? Not all of them together. So this one is talking about which one has a greater hold on it, so you need to think about electronegativity. Sulfur is 2.6, fluorine is 4.0. That means that sulfur does not pull as strong as fluorine. Fluorine is pulling those electrons very strongly, so fluorine has a greater hold. Next up, number two, building off that same thing. So in terms of polarity, the bonds in SF6 are polar. Since fluorine is much more electronegative than sulfur, fluorine has a greater hold on those electrons, right? The electrons are all being pulled towards the fluorine atoms, away from that central sulfur. But since all of these arrows have one to cancel them out, right? Like if we look at the molecule as a whole, it is completely symmetrical. You can fold it down this line, down that line, down that line, down that line, and it's even on both sides. The overall molecule is nonpolar. So the bonds are polar because an individual fluorine is pulling stronger than sulfur on the electrons, but the molecule is nonpolar because you have all of those fluorines laid out evenly, and the pulls that they have cancel each other out, like an up pull cancels out a down pull. So number three, describe the difference between the behavior of electrons in polar bonds versus nonpolar bonds. So polar bonds, electrons are not shared equally. Because for instance, fluorine is pulling on them harder than sulfur is. Nonpolar bonds, your electrons are shared equally. And a nonpolar bond, that will be when the electronegativities are very similar, like a difference of 0.4 or less. So next up, trying to erase here, it's not going very well for me. There we go. Okay, so next up we have question 4. Explain in terms of numbers of valence of electrons how sulfur in SF6 violates the octet rule. So if you remember when we are making our covalent bonds, we do it in a process like this, right? We pair up single electrons. And so in every bond, there is one electron from the first atom and another electron from the second atom. So in every bond, in every line, there are 2 electrons. Sulfur has 6 bonds around it, right? 1, 2, 3, 4, 5, 6. So there are 2 electrons in each of those bonds. So 2 times 6 would be 12 valence electrons. So describe in terms of element type and electrons what type of bond occurs between S and F. So sulfur and fluorine are both nonmetals. So the bond is covalent and electrons are shared. Kind of a definition question, but when you have nonmetals bond together, it's covalent. and they're going to share their electrons because their electronegativities are relatively similar, at least. All right, intermolecular forces. Ammonia is able to partake in strong intermolecular forces known as hydrogen bonding, causing it to stick to other molecules of ammonia. So, number 6. On the ammonia molecule provided in the box, draw the correct partial charge symbols. So I'm going to zoom in a bit. On each atom and the proper dipole moment arrow. Well, when you look at the periodic table, nitrogen is closer to fluorine, so nitrogen is more electronegative. So it's going to be pulling electrons towards itself. All the electrons go towards nitrogen in each bond. This makes it partially negative. And that makes each of the hydrogens partially positive. All right, so that's it for number 6. Partial charge symbols on each atom and the dipole moment arrow on each bond. I'm going to switch colors here to make it easier to see for number 7. It says draw 4 other ammonia molecules, showing how they would hydrogen bond with the ammonia molecule provided in the box. So like, let's say I've got another ammonia over here. So the nitrogen, remember, is partially negative over here. So to show a hydrogen bond, we are not going to draw a line like that. That line shows a covalent bond. To show a hydrogen bond, you draw some dashed line. It can be dots, it can be dashes, whichever is fine. But we need to show that the partially positive hydrogen is going to have some sort of attraction, some sort of stickiness to the partially negative nitrogen. Like that. And we want to show 4 other ammonia molecules. So we need some more NHs, NH3s. And it's important that the hydrogen is attracted to that lone pair of electrons, because that is really the center of the negativity, because electrons are negative. Okay, so since the nitrogens on the other molecule will be attracted to the hydrogens, then the nitrogen of our starting molecule will be attracted to a hydrogen as well, because hydrogen is partially positive in this molecule. All right, so that shows the attractions, the hydrogen bonding. And water does something very, very similar to this, right? That's explains all the properties of water that we've been seeing with the surface tension and cohesion and whatnot. Okay, so number 8. Given the graph displaying vapor pressure to the bottom right, which liquid would have the weakest intermolecular attractions? Okay, so vapor pressure, it's what that talks about. It's essentially how many molecules of gas are above a liquid. And in order to think about that, if something evaporates very easily, it will have a lot of gas above it. So, apologies for the siren in the background, that happens. Okay, more gas above a liquid, right? It evaporated. So if it evaporates quickly, right, let's say more evaporation, that means your liquid is less sticky. Because if your liquid is very sticky with itself, if it has very strong intermolecular attractions, it's going to be hard for it to evaporate. So you will have a low vapor pressure. Well, weakest vapor pressure. Well, first of all, if it's saying weakest, it's either going to be the thing that is the highest or the lowest. So we can cross out B and C. So choose a temperature and examine the vapor pressure. I'm going to just look on this line. So we go up, liquid D has a vapor pressure of like 60. Go up, liquid A has a vapor pressure of like 750. So liquid A, vapor pressure of 750. That's a really high vapor pressure. So it evaporates very easily. It is very not sticky to itself as a liquid. So it has the weakest intermolecular attractions. Number 9, which compound would experience the weakest intermolecular forces? So this one is kind of just going off of the fact that if you have something that is more polar, it is going to experience more intermolecular attractions. But also if you have more OH groups, you have more hydrogen bonding. So to find the one with the weakest intermolecular forces, this has 2 OH groups, so that should be pretty strong. This has 1 OH group, so not as strong as D, but still pretty strong. This one doesn't have an OH, but it has a double bonded O. This does make the molecule partially polar. All right, so this is a polar molecule. This one we said can have, has 1 spot for hydrogen bonding. So we'll have 1 OH. This one has 2 OHs. And this is a non-polar molecule, A, because it's completely symmetrical, right? It doesn't have a positive side and a negative side, which, remember, those positive and negative sides like to attract each other. So this has really nothing that's attracting it to other molecules, making butane the weakest intermolecular force. Highest boiling point. If it's harder to boil something, it needs a higher temperature. That's a higher boiling point. If it's harder to boil something, that means it's stickier. The liquid is harder to separate. So that means it must have a high intermolecular force. So that is going to be D, because D can form the most hydrogen bonds because it has more OH groups. And which compound is most likely to be liquid B? All right, so we look at liquid B. So remember how we said that liquid A has the weakest intermolecular forces because it has the highest vapor pressure, so it evaporates the easiest? Well, liquid B has the second highest vapor pressure, so it evaporates the second easiest, so it must have the second weakest intermolecular forces. We know D is the strongest, C is the second strongest, B is the second weakest, so it must be B. All right, ionic bonding and ionic compounds. So we have a crystal structure shown here where the different cations and anions attract each other. They lay out like plus, minus, because the positive particles, the cations, will attract the negative particles, the anions. So explain in terms of charge and electrostatic attraction why cations do not exist next to other cations in ionic crystal structures. So cations are positive and would repel each other, not attract. Simple as that. They're all positive, so you can't have those positive charges sitting next to each other. They don't like that. All right, list the chemical formulas of manganese 4 sulfide and manganese 3 sulfide below. Show work. So showing your work, I just mean do the drop and swap. So manganese is Mn. Remember our Roman numerals. IV is 4. So plus 4. Sulfur is a -2. Because remember, when you look at the periodic table, it needs to go 2 steps forward to get to group 18. So that's gaining 2 electrons. And gaining electrons makes you negative. So get rid of those plus minus symbols. So we get Mn2 got dragged there, S4. You must simplify if you can, so you got to divide by 2. You get Mn1, but we don't write the 1, S2. Next, manganese 3 sulfide. Remember, all this shows you is what charge this is. That's all. The drop and swap. Right. Mn2, S3. Next up, draw 2 sets of Lewis structures showing the formation of aluminum nitride, an ionic compound. So aluminum has 3 valence electrons. Nitrogen has 5. If you are drawing circles and lines here, that is wrong. That is what we do for covalent bonding. This is an ionic bond, right? Because it's a metal and a non-metal. So in ionic bonds, there's no sharing, there is transferring. So the aluminum is going to give its electrons to nitrogen. Aluminum, after the fact, will have a +3 charge because it has gotten rid of 3 electrons. The nitride ion started out with 5, but it gained 3 more. It has a full octet. When a nonmetal has a full octet and is an ion like this, we put the brackets around it and the charge goes on the outside. Nitride has gained 3 electrons, making it a -3. Which choice best describes the role of electronegativity in covalent bonding? So covalent bonding, right, that's nonmetals. And it's covalent. So co means like cooperate, coworker, together. Valent is valence electron. So you're going to have nonmetals sharing electrons because they have similar electronegativities. Yeah, like similar electronegativities, they're not able to pull away from each other because they're both fairly strong at pulling electrons. If you're talking about ionic bonding, metals have really low electronegativities, so nonmetals are able to just straight up take electrons from them. All right, so this is building off of the lab and the lab report. So researcher obtained 2 chemicals, sodium acetate and sugar, but he doesn't know which is which. So sodium acetate, we can see that is an ionic compound because there is a metal with nonmetals, and sugar is covalent. So let's see. Identify substance A as either sodium acetate or sugar. Okay, well, substance A conducts electricity when dissolved or when melted and has a high melting point. These are properties of ionic compounds. Substance B does not conduct electricity under any scenario and has a super low melting point. Those are typically covalent properties. So we will say substance A is sodium acetate because it is conductive when dissolved and has a high melting point. So that is our claim and our evidence, so we still need the reasoning. These are properties of ionic compounds and sodium acetate, which is this, has both metals and nonmetals, making it ionic. A bit of writing, but that's what you do. And once again, that's basically just your guiding thought around the lab report. Describe the types of bonds found in sodium acetate. So sodium acetate, we know, is this. So there are ionic bonds. There's ionic bonds between sodium and the nonmetals. But remember what we were learning about with polyatomic ions. Sodium acetate, this acts like one thing. This is the acetate ion. So with this, since it's negative, it will be able to bond to sodium, which is positive, and it does that ionically. But within this, those are all nonmetals sticking together. So those are covalent bonds in there. So ionic bonds between sodium and the nonmetals, and covalent bonds between the nonmetals. Okay, which of the following properties are most likely to be demonstrated by substance B? All right, so substance B was covalent, right? So right off the bat, if you remember, covalent compounds have amorphous structures typically, which means that there is no regular repeating structure. A crystal structure is a regular repeating structure. That is something that ionic compounds have. High boiling points, that's what ionic compounds have. Transferred electrons, that's what ionic compounds have. This is the only covalent one. Okay, the formula of a chloride salt is XCl3. Which group of the periodic table could X be in? You need to look and see what it's paired up with. So it's paired up with 3 chlorines. You know that one chlorine, given its place on the periodic table, has a -1 charge. So if you have 3 chloride ions, that is a -3 charge. So X, to pair up with that, it needs to be a +3 charge. So group 1 is +1, so no. Group 2 is +2, no. Group 13 has aluminum in it, right? And we know aluminum can be a +3. So yes, this is a group 13 metal because it needs to have a +3 charge. And finally, which type of elements or compounds would be most likely to have bonding described as a mobile sea of electrons? This is metallic bonding. You can also see it called delocalized, right? Meaning that it is mobile, right? They're not local, they can move around. All right, so good luck studying. I was able to do that in 24 minutes while explaining it all to you guys. So you'll have 45 minutes on Wednesday.